So I'm now going to talk about how we can use dynamic programming as a solution to the Bellman equation in order to do policy and value iteration. So let's start with the Bellman equation. And we know state value, right, the value of a state is the expectation of the future reward from that state, right? And we write that in its simplest form in this fashion, v pi of s. So the value of the state S under policy pi, and that's very important, is the expected value of the future reward. And this expression can be split into two parts. So in terms of what's inside the expectation, we can basically split it in terms of an immediate reward and a future reward. So just go through the terms one at a time then. This equation then is telling us that the future reward or the future expectation reward from state S under policy pi is given by the expectation of, first of all, the immediate reward added to the discounted future reward. And if you remember, we have this gamma function which basically means future values can be worth less and less and less as we move forward from the current step. Let's now think a little bit about expectation. How do we calculate expectation? And that's quite easy. We can just use this simple formula that we've seen before. So in other words, in order to calculate the expected value of something, what we have to do, first of all, we have to look at, in the case of a discrete variable, what values can occur. Let's say we've got several different values which can occur, and then we have to consider the probability at which those actually occur at. And then in order to calculate the expected value, we add up the product of each value with the probability it actually occurs at. So in the case of a dice, for example, imagine we've got a fair dice. The probability that we throw 1 is going to be 1 over 6 because it's got 6 sides. A 2 would be 1 over 6 again. 3 would be 1 over 6. 4 and 5 and 6. Again, this is a fair dice, so all of them would have a probability being of 1 over 6. And of course the values for these particular conditions are pretty much stated by what x is. So value of x is 1, value of x is 2 is 2, 3, 4, 5 and so on. So what is the expected value that we'll get from throwing a dice? It's easy to work it out. Basically we've got to sum up across all 6 possibilities, and what we do is we sum across the product of the value and the probability that it occurred. So in other words, we've got to sum up between 1 and 6, and each of which has got a probability of a 6th. Right, so we can just expand the sum here, so it's 1, 2, 3, 4, 5, 6, all of divided by 6. We end up with 21 over 6, so we'd end up in this particular case of an expected value coming from this of 3.5. Okay. So now let's think about the expected value of future reward g of t. In order to do that, what we've got to do is we've got to think about what's involved. You know, what pathways, what states can the system get into, and how does it get there? So we start off in the current state S, and the current state S is going to have a value of v pi of s. That's going to be the expected value for future reward from that state. And if we follow a policy pi, and that's what we will do, and this is a stochastic policy, so what this does from state S, it gives us a probability distribution over A, over the actions, right? So for a given S, we have the probability of action coming out, and generally there'll be several different actions, multiple actions that can happen. So what we'd actually have then at this point, we'd have, when we use this stochastic policy, we have various options happening, and then it's up to, if you like, the system to decide which of the possible ones is going to take. If you were adopting a greedy policy, what you'd do, of course, is you just pick the action with the largest probability. But that's just one action of many that can happen. So there's many things which can happen here, but we're just going to focus on one particular one that does happen, because that's, if you're looking at one path forward, that's what's going to happen. Then what happens is Right, okay, then we choose one particular action out of many that could have occurred, and these can all occur with different probabilities. And then given that action has then occurred, right, generally speaking, we have a transition probability as well. So given the action, we use the transition probability in order to work out the probability distribution of the future state that we get given that action. And again, this can also be and is generally stochastic. So not only have we got this stochastic process of getting an action, we've got a stochastic process of getting the end state S prime as well, right? And that will generally also lead to a reward when we go from state S to state S prime. We get the reward R from that particular transition. That's the immediate reward. And of course, then we move into this particular state that we're going to end up in some state S prime out of the set of possible states that we could have. So this state S prime has also got a value, and it's going to be the value v pi of S prime, just like it was for the original state here, v pi of S. So let's think about what's actually going on here. So we can see we've got, this is just one particular path that we could have had on any particular trial, but in actual fact there's lots of other possibilities. So we could have gone, rather than going straight to this middle action and then straight to this resulting state S prime here, we could have chosen or been basically generated this action here, depending on how the action was chosen, and it may have then gone off to a different state. We could even go to this state and then go for another state afterwards as well. Sorry, in this action, go to another state as well. So there's lots of these pathways. So therefore, starting at state S, and under this stochastic policy, pi A of S, this leads to a particular action that we're going to take from a set of available actions. And then this then leads into a stochastic transition probability. So given the action, it's going to lead to a new state, but this is also a probability, so this is a transition probability. And it will finally end up in a particular state S prime from all the possible available ones. And when we go from S to S prime, we will get immediate reward R. And when we get to the final state S prime, that is also associated with this future value as well. And we can also discount that if we're going to use a discounting factor in the way we're doing the calculations. So we can discount that with a factor gamma. So for one particular sequence then, we get a total reward given by, right, the R from the immediate transition that we get, and also this other future reward term, which is then discounted. So we got the R comes from the immediate transition from S to S prime, and we know that we've got this future reward term, which basically arises because we want to make sure we take advantage of the fact that we know the value of the state we end up in, and we discount that value by this gamma term. So that's the reward we get from one particular sequence of events that we get. But there's lots and possible sequences of events. In fact, there's actually a joint probability of where we're going to end up, and that's given by the stochastic policy, so the probability distribution due to the policy, multiplied by the probability distribution due to the transition probability. Right, so we've got this product of two terms giving us the joint probability of where we're going to end up, which is then going to be just written down here as pi A of S multiplied by P S prime given S and A. So, given the future reward that we have, that we've calculated, and given the probability that that will occur, we can use the definition of expectation, because now we've got, this is now our value, and this is the probability that that value occurs. And if we want to actually calculate the expectation, we now have to sum across all the actions, right? Because this depends on A, and this depends on S prime, and also all the state S primes. right? So in other words, it's quite simple. We're just looking at this formula. We can immediately substitute in the two parts that we've actually got. This constitutes the value part, right? The r plus gamma v pi of s prime, and this represents the probability that that occurs as this joint probability p a of s multiplied by p s prime s given a. Okay, so that's where this is the probability term. It goes here, and this is the value term. It goes here, and you can just see that this is exactly the same form as the expectation that we calculated when we were also doing things with simple things like dice. So that gives rise, if we split this up, split the sum up, so we're actually just summing across the actions, and we only need to have the term with the policy in there, of course, because it's basically got the action at the front of it, so it's action given state, and then we split, and then in the second part, then we actually put just across the transition probability here. So we can see, just on the basis of looking at things in a simple way like that, we can come up with this equation saying the value of the state under policy pi is given by, well, obviously it's the expected expectation of future gain, which is given by the sum across all actions of the policy multiplied the sum across all future states of the transition probability multiplied by the total reward that we're going to get. And just to think about it, when we actually look at what this is actually computing, we see it's actually computing across all actions, because it's summing across all actions here, and it's summing across all future states here. And quite often you'll see these things expressed in terms of what we call backup, and that's really, you know, how wide, how deep is it actually looking at the structure of what's going on at the state space. And we see what's happening then when we start at state S. We do a full width backup in as much as we look across all actions. So that's these little black dots here, they're all actions, and it also looks across all future states as well that can actually occur. So that's this region here constitutes one computational step, so one backup it's called in this way of looking at things. So given that we've got this Bellman equation, which lets us calculate the state value, right, evaluated under a particular policy, and of course if we change the policy, what we're doing is we're changing this probability distribution. So we change how action probability depends on the state we're in, then obviously we're going to change the value. And of course if we change the transition matrix, we change it as well. Well, that's also going to make a difference. This version above actually is a slightly more complicated version, because it's also it's basically using a transition matrix which has also got the joint probability with the reward in there as well. So you might see this form occasionally. So if you see this form, we have to sum across not only future states but also rewards as well. So this version here is the simpler version that we just discussed, and this just sums across all actions here, across policy, and all future states. This version here, like I said, is using the joint probability for the transition function, the joint probability of future state and reward. But because we can always marginalize things by summing things out, that's not a big deal. It's just this formula is a little bit simpler to use. So this basically lets us calculate then the value for an arbitrary policy. And what we could do is we could start off with an initial approximation of what we think the policy is. And this is a good way to judge, judge what the value is. And this is a good way then to judge how good policy is. In fact, we can actually then use this formula that we've got here in order to update what the value is. So by repeatedly using this formula, we can iteratively start off with an approximation of what we thought the value function was for each state. In fact, it could be completely wrong to start with. But if we repeatedly use this formula, we see that it's making use of it's looking at other states when it's updating the one it's looking at. We can iteratively run this over the data and actually get the thing to update and converge to hopefully a good solution. So a full iterative backup then would be written like this. Now all we're saying is, we're just saying now the updated value function, or the updated value at step k+1 of the state, is effectively just the value function that we had before. So we can just update the value of the state on the basis of doing this calculation and using what we have for the current values of the states as well. Again, P S given S and A, that's the probability of the next state S prime given the current state the current state S and the current action A. Policy, of course, is represented by probability of the action given the state, and R is the immediate reward that we get from taking an action, and gamma is the discount factor, so how much we're going to start discounting future reward. So classical solutions to this Markov decision process that we've actually just looked at are known as dynamic programming methods, and as you can see, they can be used to calculate value functions. They are iterative methods. You just apply it and apply it and apply it until finally you've got a converged solution. So in other words, you need many sweeps through in order to improve it. So we'd start off with a very poor value of our estimate of the poor estimate of the value. We'd run a sweep, we'd run a sweep, we'd run a sweep, we'd run a sweep, and slowly, but hopefully surely, we end up with getting a good estimate of what the actual value is. Like I said, that's just by applying this formula again and again and again. Of course, important to notice, we do need to know what the policy is, and we do need to know what the transition function is. And this is what the pseudocode looks like from Sutton and Bartow. So the important thing is we start off with the policy pi that we wish to evaluate. We're going to initialize our value function to some sensible value. It could also be, could be something quite tiny. And then we've got a loop basically. And then we see that there's a loop across each state. So for each state, well, first of all, we make a copy of the value function, and then we say the value function is then given by the equation we just discussed. So the value function S for state S is then given by the sum across all actions of the policy multiplied by the sum across all future states and rewards of, in this case, it's the joint transition function with future state and reward multiplied by, this is the total reward, which corresponds to having immediate reward, and here's the discounted future gain as well. And then all it's doing in this particular line, looking for the delta, it's just comparing what the value was before with the value we get now. And if it's basically quite tiny, then we say then that's pretty much finished.